Hello everyone. Let's talk about atomic spectroscopy. First, atomic spectroscopy deals with absorption, emission, fluorescence of radiation. If we talk about atomic absorption, we use atomic absorption spectroscopy, and we use AAS to represent that. If it's atomic emission spectroscopy, we use AES. E means emission, S means spectroscopy, A means atomic. If we talk about atomic fluorescence spectroscopy, we use AFS. Second, this method deals with one by one individual free atoms. That's why we call that atomic spectroscopy, which is different from molecular spectroscopy. In molecular spectroscopy, as we learned before, you got a broad band. But in atomic spectroscopy, what we got is one by one line spectrum. You got very, very narrow lines. Very, very narrow lines. And the third, each element has its own very special spectrum, just like a fingerprint of each person. By these specific properties, those specific spectral line can be used for elemental analysis. That means quantitative analysis, but also means qualitative analysis. So that means this method, we can do both work together. To get those free atoms, a substance must first decompose into atoms. But how? To get free atoms, you must break and damage the molecules. We need a very high energy. Here are common ways. You can use flame, and you can use a stronger one, furnace, and you can even use an even stronger one, strongest one, that is a plasma. The temperature range can be 2000 to 8000 Kelvin temperature. That means we measure the concentration of atoms in the vapor, and not like a molecular spectroscopy. We measure the molecules in liquid solution. Here we measure the atoms in vapor. Such methods are very common. Actually, it's the most common method for the analysis of metal and other elements from ppm to ppt level. That's why we call that elemental analysis. Sometimes we call that metal method. Because those methods are related to transition of electronic state, there will be no chemical bond because no molecules. Therefore, there will be no vibration state transition. No chemical bond, no vibration, right? That's why we got separated line spectra. These spectra are related to electronic states of outermost layer rather than inner layer. That's why we got the spectrum in the UV, ultraviolet, and visible range. If we measure the inner layers, we can also get the spectrum. That's another elemental technique. We call that X-ray spectrum. In the future, we can touch and discuss this technique briefly. Some of you are doing research with that. If we only test the vibration or rotation for molecules, that's what we learned in last chapter. That's in another range of the light. That's infrared spectroscopy. As you can see, detecting different transition state, you have a infrared range, you have UV range, you have X-ray range. The instrument scheme is similar to what we learned in molecular spectroscopy. This is setup of a molecular spectroscopy. You have a radiation source and go through the wavelength selector, then go to your sample container. So which can be a cuvette. Then the light goes through the cuvette, got the detector. So if it's fluorescence, the detector will be here. However, for atomic spectroscopy, you cannot directly put the cuvette here because you must change the sample from liquid or solid into individual atom, right? So that's why we have another setup. We need the atomization setup. In that case, in the radiation way, you got individual atom here. Your sample is pumped to the room and got atomized. That's a very important difference between molecular and atomic spectrometry. Here is the electronic transitions. You can see from 1s to 2s, 2s to 3s, depending utmost share. So then you will have a different kind of transition. And as a result, this is a very typical atomic spectrum. You can see different atoms will have a very sharp of peak at a different position. Keep in mind, one atom can have multiple spectrum line. For example, iron is here, iron is here, iron is here, iron is here also, and the chromium is also. And because as we can see from the electron transitions, they have a different stage. Electron transferred to different levels. That's why you got different one. Again, here's the feature I want to repeat. First, the sample must change to gas phase atom or ions. And second, because it's individual atom, there's no vibration or rotation energy stage. That's why there's no band. No band. And only electronic transition occur. And also you can see the range is between the UV range. You got a spectrum with a limited number of narrow spectrum lines. Here's the typical instrument setup. This is the scheme. If it's the atomic absorption, similar to what we learned in molecular absorption, you can see the radiation is a hollow cathode lamp, HCl. The light goes through your individual atom area, then the light will decrease the intense because absorption. As a result, you measure the change. You use Beer's law to detect how much change. You also have this formula to detect. But if you are using fluorescence and you cannot do that in same line, which is exactly same as the molecular fluorescence. You can see here there's a right angle here. And you got a laser, you excited the atom, and then the atom jump back and release another light, but at a different direction, you detect that. That's fluorescence. This is what happened for fluorescence. And the first one is absorption. And you directly check how much energy they absorbed. Oh, first one is here, absorption. And the blue line here is actually this is the emission. Emission is in first case. Actually, when you got the atom, if the energy high enough, then at the outermost area its temperature is extremely high, or you use the plasma. In that case, the atoms got excited by itself through the strong energy. And when they jump back, they will release the light. You just detect how much light is that. So you can see it's similar to other technique. The first one, top one and the bottom one, emission and the fluorescence, both are emission spectrum. And the middle one is the absorption spectrum. This is what we need to know at the beginning. Here's the typical comparison between molecular spectrum and atomic spectra. You can see one is very sharp, another is very broad. The bandwidth for molecular spectrum can be as wide as 100 nanometer and even more. But for atomic spectrum, for the gaseous atom, actually the sharp line can be 0.001 nanometers. And because these sharp lines make the elements very difficult to overlap, you can simultaneously measure many elements. How many can we detect? If we use the best atomic spectroscopy, for example, ICP technique, we are going to discuss that later. And also we have this instrument we are going to do the lab this semester. So you can simultaneously actually measure 70 elements. Keep in mind, we only have around 110 elements. Right now, you can directly use that to detect 78 elements. That's most powerful elementary technique to do the analysis for elements, and both for quantitative and qualitative.